Shall I begin? So I will share the link once again for new people that may have joined. If you have Git Bash, you can copy paste this and Git clone the repository. If you are on Linux or if you have Git Bash on Windows, otherwise you can download the zip file, or you can open directly on GitHub. You can only open. You cannot run code here. You can only view. Yesterday, you were introduced to TensorFlow, which is a deep learning framework, and many of you may have had prior exposure to TensorFlow even before that. But I hope most of you will be new to Pytorch. Okay, so these two, both Pytorch and TensorFlow, are both open source deep learning frameworks. So let us go to the websites of Pytorch and TensorFlow through the links here. Okay, so pytorch.org. So from research to production. So they claim that it is an open source machine learning framework that accelerates the path from research prototyping to production deployment. So it's an open source machine learning framework. What about TensorFlow? TensorFlow.org. It also claims to be an end-to-end open source machine learning platform. So both are open source end-to-end machine learning platforms, and more specifically for deep learning, because there are other platforms for machine learning in general, but these two are kind of the only deep learning platforms. They are, even if there are some other deep learning platforms, these TensorFlow and Pytorch are by far the two most popular deep learning frameworks. There used to be some other framework, but most of them have ceased development. But these two are very popular. So the first question is, how do we choose Pytorch versus Tensor? Which one to choose? As you might know, TensorFlow based on Theano is Google's brainchild, born in 2015. TensorFlow is supported by Google, while Pytorch is a close cousin of the Lua-based Torch framework, born out of Facebook's AI research lab in 2017. Okay, so TensorFlow is supported by Google, while Pytorch is sponsored by Facebook. And we see that TensorFlow had a head start of 2 years. It was released in 2015, but Pytorch came 2 years later. But when Pytorch was released in 2015, a lot of researchers began to shift to Pytorch. And the main reason why researchers shifted to Pytorch was due to the difficulties in using TensorFlow version 1. But TensorFlow, they released a major upgrade by the end of 2019. It was called TensorFlow 2. That release, TensorFlow 2, addressed most of the difficulties in using TensorFlow. The library was made much user friendly, and it was much easier to use. So now we have TensorFlow version 2. So we cannot say that TensorFlow is more difficult to use than Pytorch. Both are very user friendly. Pytorch continues to dominate in research, because most of the researchers shifted to Pytorch when it was released, and perhaps they continued to stick with Pytorch rather than going back to TensorFlow, even though TensorFlow 2 had a much more friendlier interface compared to TensorFlow 1. Now, as of now, the situation is that Pytorch dominates in research and TensorFlow dominates in production. So let me try to substantiate the claim that Pytorch dominates in research. I have given some links here, and let us go through the links to validate this claim that Pytorch dominates in research. First link compares the number of conference papers which are implemented in Pytorch versus TensorFlow. Okay, so this is the total number of Pytorch papers for different conferences, different prestigious international conferences, ICLR. You see that this is the percentage of Pytorch papers of the total TensorFlow and Pytorch papers. Okay, so here we see that in ICLR 2022, almost 84% of the papers were in Pytorch, and even other conferences also, a majority of papers are in Pytorch. Now the second graph shows Pytorch versus TensorFlow of the total papers. So here we take one conference, this conference, Pytorch papers were 33, TensorFlow 4, so on. So you can see that in almost all conferences, there are more papers in Pytorch than TensorFlow. Okay, and by a large margin, I think this is for NeurIPS 2020, very prestigious conference. Similarly, other data also shows a similar trend, that much more number of prestigious conference papers are implemented in Pytorch. Okay, so that is one evidence that Pytorch dominates in research. Now, if you go to this site, paperswithcode.com, paperswithcode.com website, paperswithcode.com is an attempt to open source all research publication. If you scroll down, you will see that more number of papers are in Pytorch rather than in TensorFlow. And this course, Stanford's Natural Language Processing course for 2022. This course uses Pytorch. I read somewhere here that this course. Okay, so this through lectures, assignment, final project, the students will learn the necessary skills to design, implement, and understand their own neural network models using the Pytorch framework. So Stanford courses are using Pytorch rather than TensorFlow. Okay, so this course is on natural language processing, and if anyone wishes to undertake some research in natural language processing, this is a good course. Natural language processing is another area that deep learning has made such a big impact. Machine translation of language, chatbots, so word summarization, etc. So, and there are some people who believe that deep learning is going to have more effect in natural language processing than with computer vision. But I think that few people among us undertake research in natural language processing compared to computer vision. Maybe all of us have learned DSP, image processing. So the natural next step is computer vision. But I think the entry barrier to natural language processing is also very little. Even they are also using deep learning techniques which apply to all areas. And if you are into deep learning, this is Hugging Face is a site that contains lot of state-of-the-art deep learning models like BERT and GPT for natural language processing. You can access all the recent models, data sets. I think when I went through this, what I felt is that most of the models are for NLP. So here also, if you go through the models, you can see that a vast majority of models are implemented in Pytorch rather than TensorFlow. Okay, and speech brain is another resource for speech processing applications. A Pytorch powered speech toolkit. So it has out-of-the-box models for speech recognition, speaker recognition, speech enhancement processing, and all. So this also is a Pytorch powered toolkit. And you may also have heard about Fast AI. Fast AI is actually a wrapper around Pytorch that helps you get started with deep learning quickly. Fast AI, fast.ai. They have a very popular course also. So on the other hand, TensorFlow dominates in production. In deployment, it is TensorFlow that dominates. So let us take a look at the Stack Overflow Developer Survey 2021. So this is the result for other frameworks and libraries. The most popular frameworks. So there are many categories. I have directly provided the link to these other frameworks and libraries where both TensorFlow and Pytorch appear. So the most popular one is .NET framework, followed by NumPy, Pandas. Now here comes TensorFlow, and Pytorch is there was Pytorch here. See, Pytorch is somewhat lesser, used by fewer number of developers. Okay. So Google has developed a variety of tools that makes end-to-end deep learning development possible, like TensorFlow.js. Which makes it possible to develop and train machine learning models using JavaScript, so that web developers can develop and train machine learning models. And there is also TensorFlow Lite, which allows model deployment on mobile and embedded devices. Let's take a look at TensorFlow Lite. Okay, so it's tensorflow.org/lite, TensorFlow Lite, that is used to deploy machine learning models on mobile and IoT devices. So it says that TensorFlow Lite is an open source deep learning framework for on-device inference. So inference is when we have already trained the network and we are using the network. Okay, so that's what inference means. And Google has also developed some development boards which can be used for do inference on embedded devices. So this is how it works. We pick some model written in TensorFlow. So convert the TensorFlow model into a compressed flat buffer with the TensorFlow Lite converter. We convert that to TensorFlow Lite and take the compressed .tf Lite file and load it into a mobile or embedded device. And then we quantize by converting 32-bit floats to more efficient 8-bit integers. Maybe for small embedded devices, 32-bit floats need to be converted to 8-bit integers. And Google has also developed these edge TPUs, edge TPU devices, which are tensor processing units. Edge TPU. They are Google's purpose-built ASIC designed to run inference at the edge. As I said, inference is when where we have already trained the model and we are only using the model for prediction. Okay, so that's what inference is. And to run inference at the edge in the sense that we are doing the inferencing right where the data is generated. Maybe we have a small embedded system for face recognition. The prediction is done on the board itself rather than sending it to some cloud or server. The inferencing is at the edge. And Google has built some ASICs for the purpose for running inference at the edge. And if I click on this link, buy on Google Store, will be taken to a site coral.ai/products. Coral is a company under Google. So they have many products which helps you to bring local AI to applications from prototype to production. These are all development boards from Coral. These boards. There are many boards. There's a development board. It's a single board computer with a removable system on module featuring the edge TPU. And you can see that the supported framework is only TensorFlow Lite. Then there is a USB accelerator. Then there is a dev board mini. It's also a single board computer featuring the edge TPU. So this is the TPU. This board has like the main processor, and there is a TPU or tensor processing unit. What I understand is that these tensor processing units are like GPUs, but even more specialized to run TensorFlow models. the supported framework is again only TensorFlow Lite. So if you want to do some inferencing on embedded devices like this, these are like Raspberry Pis, but specialized for inference, machine learning inferencing. And these boards are also very low cost. But when I try search, I think these boards are not yet available in India. Maybe you can import from US, but even a even smaller board is coming. So it supports TensorFlow Lite and TensorFlow Lite for microcontrollers. So what it is clear that Google has invested heavily in deep learning and it is ensured that it has a product for every relevant area of the deep learning workflow. And finally, let us compare the Google search trends comparing TensorFlow and Pytorch. This is the worldwide result for the past 5 years. Let's make it past 1 year, past 12 months. So these are the worldwide results. But now you see that more people are searching for Pytorch than TensorFlow. So the Google search might include everything, researchers, developers, and all. So let us try to get the results for India in past. But in India, still more people are using TensorFlow than PyTorch. TensorFlow, no, very recently on January 30 to February 5 week, more people have searched for PyTorch rather than TensorFlow. So anyway, uh, this gives a rough idea only that we can conclude that PyTorch dominates in research and TensorFlow dominates in production. That's only a rough guideline, and I summarize that you are not making a mistake in choosing either framework. Either framework will do. And one thing I want to emphasize is that the two are very similar. So if you have learned how to use PyTorch, it it, it is a very easy task to switch to TensorFlow and vice versa. So okay. So any questions?
Arun, do you have any other platform which happened to cease by this time?
Yeah, though most of the other there were many other platforms like Cafe, Theano, Torch. They are all subsumed by these two. Okay, so now moving on to installing PyTorch. I'm assuming that all of you have the Anaconda distribution of Python. If you are planning to work on uh, deep learning or machine learning or even any scientific or engineering application, the Anaconda distribution of Python is the recommended distribution because it includes all the packages that we need for scientific and engineering application. If you install the official version of Python, you will have to install all the additional packages separately. But with Anaconda, all these packages comes in a single install, so that allows you to get started quickly. So you can install the Anaconda distribution of Python from anaconda.com. Go to products, individual edition. You can download the Python distribution. This distribution includes many scientific and engineering packages like this Jupyter, SciPy, Spider, Numpy, all these. Actually, TensorFlow and PyTorch are not included. They also work fine with the Anaconda distribution rather than the official Python distribution. Assuming that you have installed this Anaconda distribution of Python, you can install PyTorch by going to pytorch.org again. So click on start locally. You can select the version PyTorch build. The latest version is 1.10.2. Then select the OS, whether it's Linux, Mac, or Windows, and select the package Conda pip. If you are using Anaconda distribution, the package manager is Conda. If you are using the official Python, the package manager is pip. Stable, Windows, Conda, and the language. You have to decide whether you have an NVIDIA GPU on your computer. So if that is available, select the CUDA version. This is the more recent one. So select 11.3. And corresponding to all these selections, you will have the command. You simply have to copy paste this command and run the command in Anaconda prompt. Go to the Anaconda PowerShell prompt. So you get this Anaconda PowerShell prompt when you install Anaconda. You have to simply copy, paste, and run this command. You can see that the command is conda install Pytorch, Torch Vision, Torch Audio. These are two additional libraries. They are also installed. Pytorch, Torch Vision, and Torch Audio are installed. Along with the CUDA toolkit. This is assuming you have an NVIDIA GPU on your computer. The CUDA toolkit is also installed. If I select a CPU, this will be missing. And this -C Pytorch means the channel is Pytorch. There are many repositories from which you can install packages in Anaconda. So this channel, the place from where these packages are downloaded, they are called channels, and that channel is Pytorch channel. Okay. So, but before that, before installing Pytorch like that, I recommend you to create a new Conda environment by using this command. Okay, rather than installing Pytorch in your current environment, it is advisable to create a new environment. And a Conda environment is like an island. It's like a sandbox. Okay, and it's advisable to use separate environments for each of your projects so that there will not be any conflict with other packages. You can create a new environment like this. Conda create --name my n. This is the name of the environment. You can give any name like deep learning, Pytorch, like that. And this option --clone base tells Conda to clone the base environment. When you install Anaconda first, you will be in the base environment. So when you clone the base, you will have all the packages in the base environment in your new environment also. Okay, so here I am creating a new environment name myn, and in that new environment I am putting all the packages that I already have in the base environment. Okay, otherwise you can do that. All the necessary commands required to manage Conda environments I have linked here. Now, so after that, you have to activate that environment, and then you have to install Pytorch in the new environment. So for example, I am in base environment now. I have an environment called DL where I have Pytorch already installed. Conda activate DL. So that will activate the new environment. So I am in a new environment. The packages I also have another environment named DL1. Conda activate DL1. So I have three environments. The packages in these three environments are different. They do not interfere with each other. They are like three different islands. Okay. So otherwise that can cause problems. So when you install Pytorch, that might upgrade some packages and downgrade some other packages already installed, and that might cause some other package to raise some errors. So to avoid that, you can create a new environment first, and then activate that environment, and then install Pytorch in that new environment. Okay. On this computer, I have a small GPU, 2 GB NVIDIA GPU is there. So I install the GPU version. If you don't have GPU, use the CPU version. And if you are planning to buy a computer for deep learning, always buy a computer with NVIDIA GPU only. Okay, so here you see only CUDA. Other GPUs from other manufacturers are not supported, not only in Pytorch but also in TensorFlow. So AMD has some GPUs, but when I select that ROCm, you see that ROCm is not available on Windows. So having installed, let us first import Pytorch. Import the command is import torch. Even though the package is Pytorch, the command is import torch. I think I started from a different base environment where there is no Pytorch.
ആയിരിക്കും.
So you see that the
അരുൺ സാർ, ഒരു ഡൗട്ട്. ഈ കുഡയുടെ 2 വേർഷൻസും എല്ലാ NVIDIA ആർക്കിടെക്ചേഴ്സിലും കോമ്പാറ്റബിൾ ആയിരിക്കും? GPU വേർഷൻസ്
അല്ല, നമുക്ക് ഇത് ഇവിടെ നോക്കാം, നമുക്ക് ഏതാണ് അതിന്റെ വേർഷൻ എന്നുള്ളത്. ഇവിടെ സിസ്റ്റം ഇൻഫർമേഷൻ, ഇവിടെ ഡ്രൈവർ. So we have imported Pytorch. So everything starts with a tensor. So we'll take a deep dive into what tensors are and how to work with tensors in Pytorch. Okay. So this word tensor may have different meanings in mathematics and physics, but in a deep learning context, a tensor simply means a multi-dimensional array. Simply is a multi-dimensional array, but compared to Numpy arrays, there are two major advantages for tensors, be it Pytorch tensor or Tensorflow tensors. The two advantages are tensor operations can be performed on GPU, and secondly, these tensors support automatic differentiation, which is important in deep learning. So otherwise, they are same as Numpy arrays. The two advantages are these operations on tensors can be delegated to the GPU, and secondly, we can compute automatic differentiation. We'll come to that later. So these are the two advantages. Otherwise, it's simply a multi-dimensional array like a Numpy array. So let us create a tensor first. So command is torch.tensor. That's the name of the function. And within the parenthesis, you have to give the elements as a list. In square bracket, the elements are separated with comma. So let me run that cell, and that tensor has been created. So let me display the output also. Control N. So the tensor X has been created. Okay. So every tensor is a grid of elements of the same type. Okay. Unlike Python lists, which are very flexible. Each element of a Python list can be of different types, but all elements of a tensor are constrained to be of the same type. And Pytorch provides a large set of numeric data types that you can use to construct tensors. Pytorch tries to guess a data type when you create a tensor, but we can also specify the data type. Let us see some examples. Let us create three tensors, x, y, and z. All are one-dimensional tensors. Here x was also a 1D tensor. We can create multi-dimensional tensors also. So here also x, y, and z are 1D tensors, each having two elements. And we can print the, here we are printing the data type. So here we are not specifying the data type. Here also we are not specifying the data type. But in this third case, we are specifying the data type to be float16, torch.float16. Okay. So you see that the data type of x is torch.in64, and for y, even though we didn't specify a data type for y, the data type is chosen as float32. The default data type is in for a torch tensor is 32-bit float. Unlike Numpy, where the default type is float 64. So here it's only floated. Perhaps to work better with GPUs, we have a smaller floating point representation. Here for Z, we specified the data type. That is, so Z is a float 60. And there are a number of data types, integer and floating point types are available, not just the basic Python types. For example, Python has only one float type, but tensors have many different float types. Float 16, float 32, float 64 are all there. Similarly, int also, many different data types. So when operating with arrays of different types, the type of the resulting array corresponds to the more general or precise one, a behavior known as upcasting. So here, X is a int type tensor, Y is a float type tensor. So when I add X and Y, W is a float array. So X has been upcasted to float before the addition. Okay, so but X is a int array, a int tensor, and if you try to assign a real value to an element of X, what happens? See that the integer part is truncated. Okay, so so the 2 points that you should remember is all elements of a tensor, they have to be of the same type. That is because of performance consideration. A list is very flexible, but the price to pay for that flexibility is degrade performance. For when we are looping over the elements of a list, Python will first have to determine how many bytes to jump to access the next element. But no such issues here. The data type of all elements is fixed. So Python doesn't have to look at the type for each element to determine how many bytes to jump to access the next element when we are looping over a tensor. We can also create 2-dimensional tensors. So this is how you create a 2D tensor. Each row has to be enclosed in a pair of square brackets. So I have 2 rows here, and the entire tensor has to be enclosed in another pair of square brackets. Okay, so this notation is a little cumbersome for those coming from MATLAB. In MATLAB, the notation to create matrices were neat, but this is cumbersome. But anyway, also you should remember this is exactly the same as in Numpy. Those who are familiar with Numpy, all these operations are exactly the same. And if you are not familiar with Numpy, this can also be considered as a tutorial on Numpy. Just have to replace torch.tensor with np.array. All these commands will work with the Numpy also. So that is one big advantage of Pytorch compared to TensorFlow. There is very much similarity with the Numpy. Almost all the attributes and methods are same. They have the same names. So it's very easy to work with, to exchange information with Numpy and other libraries in the general Python ecosystem. So we have created a 2D array like this. Each row in a pair of square bracket, each element separated by comma, and as a whole, the tensor is enclosed in another pair of square brackets. So now let us look at some attributes of this tensor. So ndim is one that gives the number of dimensions. It's a 2D array, so x dot ndim is 2. X dot shape will give the shape 2 by 3. It's a 2 by 3 tensor. X dot t will transpose. Transpose the tensor. And there are many functions for creating tensors. Rather than entering each element one by one, there are many functions which we can use to create tensors. One is zeros. Torch.zeros 4. That will create a tensor of all zeros for 4 elements, all zeros. Torch.ones is another one. Torch.ones 2, 3 will create a 2 by 3 tensor of ones. This is the shape 2, 3. So we have a 2 by 3 tensor of all ones. Torch dot full. We have to specify the shape here 2 by 3 and the constant value that is to be filled. So torch dot full 7, that will give a 2 by 3 tensor of all sevens. Okay. Now, if you want to initialize an array, it may be maybe perhaps to store your result of some future computation. We can use torch.empty 2, 3. So that doesn't do any initialization. So these are some random values lying around in those memory locations allocated for X. So, this is faster than torch.zeros. When you initialize some array, when you want to reserve some space for storing your result, you can use torch.zeros to reserve space. But for that command, Pytorch has to specifically write zeros in all the locations. But if you are sure that all the locations will be filled by some computation, you can use torch.empty, which is faster. You just the locations are reserved, nothing is written. So this is faster. Anyway, hello. You can create random tensors, torch.rand 5, 3. So that will generate a tensor having size 5 by 3 filled with random values. These are uniformly distributed random numbers in between 0 and 1. Uniformly distributed random numbers can be generated using torch.rand, and it can have any dimension. Here we are generating a 2 by 3. Now, torch.rand n, here n stands for normal distribution or Gaussian distributed. You can generate a Gaussian distributed random tensor using torch.rand n 5, 3. So these are samples from standard normal distribution. That means they have these are drawn from a distribution with 0 mean and unit variance. You can also generate random integers, torch.randin. If you want to generate numbers between 10 and 20 and having shape 5 by 3, you can use randin between numbers between 10 and 20 shape. And if you already have some array, I have a tensor X, I want another array, another tensor W having the same shape as X but with zeros. You can use zeros like. So W is torch.zeros like X. So W will have the same shape as X but will have all zeros. It will have all zeros. Torch.arrange. If you are familiar with Numpy, all these are in Numpy also. Torch.arrange 0, 1, 0.2. So the format for arrange is start, stop, step. So the start value is 0 because start value is 0, stop is 1, and the step is 0.2. So 0, 0.2. And remember that the stop value is not included. So that's why we don't see 1 here. We don't see 1 here. So in torch.arrange, start, stop, step. And alternative to arrange is linspace. Torch.linspace. I want an array between 0 and pi with 10 elements. Then I can use torch.linspace. Torch.linspace. An array, a tensor X has been created. Again, you see the easy interoperability with the Numpy. I am specifying a Numpy value here as the stop value. I mean the last value. Difference between arrange and tensor is that in arrange you specify the start value, the stop value, and the increment. In linspace you specify the start value, the stop value, and the number of elements. The increment is calculated automatically. and also mathematical functions apply to entire tensor. So y equal to torch dot sin x will apply the x is an array. X is an array having 10 elements, isn't it? So this command will compute the sign of each element of x and put it in y. So y will also be a 10 element tensor. So we don't need any for loop. Again, like NumPy or MATLAB. So these 10 torch, Pytorch functions, they take array tensor arguments. And tensors can be plotted using MATLAB. So now that we have x from 0 to pi and y equal to sine of x, where x and y are both tensors, we can plot x comma y. X comma y, you see the sign from 0 to pi. Okay, so x and y are tensors, but they can be passed to the plt.plot function tensor. It accepts tensors. So that is good. So Pytorch allows you to work in the Python ecosystem. It works easily with other libraries in the Python ecosystem more than TensorFlow. Also remember, mathematical operations are performed element-wise. Mathematical operations are performed element-wise. Create 2D arrays x and y. X and y. Let me create x and y first. X is 1, 2, 3, 4 and y is 5, 6, 7, 8. Now if I do x into y, what does is the corresponding elements of x and y are multiplied. The corresponding elements of x and y are multiplied. Similarly for other operations, for division, each element of x is divided by the corresponding element of y, x plus y. Corresponding elements of x and y are added. Now if you want to do matrix multiplication, x is 2 by 2 and y is 2 by 2, and if you don't want to do the matrix multiplication, the operator is this at x at y will do the matrix multiplication. Okay, and Pytorch also has the broadcasting feature borrowed from NumPy. Exactly the same rules apply here also. So normally when you add two arrays, we expect them to be of the same size, isn't it? Here in this example, x and y were both 2 by 2 tensors. But by this broadcasting mechanism, Pytorch allows you to do mathematical operations between different sized tensors. Here we see an example. X is a 2 by 2 tensor, but I want to add with this one-dimensional tensor having 2 elements. A mechanism called broadcasting allows you to do that. Without any error. Okay, x is 2 by 2, while this is simply a 2-element one-dimensional array. But that is the addition happens without any error. What Pytorch does is it expands the array, the tensor having fewer dimension to match that of the other tensor and do the addition. It's like putting another row of 2, 3 and then adding. Okay, so but there are very precise rules for broadcasting. It does not allow mathematical operations between arbitrarily sized matrices arrays, and you have to go through the rules, but the rules are exactly the same as the broadcasting rules in Numpy. Now tensors can be indexed, sliced and iterated over, much like Python lists and NumPy arrays. So if you are familiar with operations on list and NumPy arrays, indexing, slicing in Pytorch is also exactly the same. So we create a tensor A in torch.arrange 10. So 0, 1 to 9, 10 element tensor, and we can index. And if you want to access one element of A, we can do indexing. So A of -2. What does that mean? We know that in Python we can index backwards also. Starting with -1. This is A of -1. This is A of -2. A of -3 and so on. So we can index backwards also. So A of -2 is 8. A A of minus 2 is 8. But you see that even though A of minus 2 is a single value, what is returned is a tensor. Tensor 8. It cannot be used in place of some floating point value. It's returned as a tensor. If you try to okay, so to get the actual value, when your tensor has only a single element, we can use this method called item. Okay, so here A of minus 2 is a single element only, but what is returned is that single value as a tensor. But if you apply the item method on that, you will get the actual value of 8. Similarly, we can use slicing, again same as in Numpy and list. If I have B, I have created A is this 0 to 9, and if I can slice A to create a new tensor B. B is equal to A 2 colon 5. This means take elements of A from indices 2 to 5. 2 to 5, but 5 not included. So it will take the elements at indices 2, 3, and 4. Okay, so when you are slicing, the format is start colon stop. I am using start colon stop only here, but the element at index stop is not included. Element at start index is included, but element at stop index is not included. So A2 colon 5 will return the elements at indices 2, 3, and 4. And let us see B. It's expected B has elements 2, 3, and 4. And one thing you should remember is a slice of a tensor is a view into the same data. So modifying it will modify the original tensor. Okay. So warning here, if I modify B is not there. When in creating B, there was no memory copy. No memory copy happened when we created B. B simply Pytorch created a new reference to A. So they share the same memory, and modifying B will modify A also. As we can see here, B0. B is this. I make B0 99, and if I print the value of A, you can see that A is also modified. A is also, because B0 was A2, isn't A of 2, isn't it? So modifying B of 0 modified A of 2. So this is only a slicing returns a view rather than a copy. And if you want a copy instead of a view, you should use the clone method. That will do a memory copy. If C is equal to A dot clone, then C actual data in memory is copied. And then if I change C of minus 1 is 100, we can see that A does not change. C of minus 1 is 100. I made the last element of C 100, but that hasn't changed A. Why? Because C is a clone of A, and actually data was copied in memory. Multi-dimensional tensors can also be indexed and slices. So let's create a multi-dimensional array. First we create a 1D array, torch.arange 25. Then we apply the reshape method to shape it into 5 by 5. So we have this tensor. Torch.arange 25 will create a 1D array from 0 to 24. Now this will reshape it into 5 by 5. Okay, so to access a single element from a 2D array, we need two indices. A 2, 3 is what? 1, 2, 3 is 13. So remember, in Python, indexing starts with 0. So this is 0, 1, 2. Then 3 is 0, 1, 2, 3. So it picks out 13. Again, you see that it is single value only, but returned as a tensor. If you want the value itself, you have to apply the item method. A of 3 will return 2D array. When we give single index, it extracts entire rows. When slicing multidimensional arrays, you must specify a slice for each dimension of the tensor. I am slicing this 2D array like this. A 1 colon 2 colon. This means all rows of A starting from row 1, all columns of A starting from column 2, row 1 to the end, column 2 to the end, row 1 to the end എന്ന് പറഞ്ഞാൽ ഇവിടെ തൊട്ട് column 2 to the end എന്ന് പറഞ്ഞാൽ ഇത്. So this subarray should be returned when you do this slicing operation. Isn't it clear? Slicing operation. I am omitting the stop index here. So that means go till the end. From row 1 till the end, from column 2 till the end. Okay, so this subarray is returned. Again, remember, if you assign it to some variable, it's only a copy. Modifying that will modify A also. Now for reshaping, we can use torch.reshape or torch.view. Earlier we used the torch.reshape. Instead of torch.reshape, we can also use torch.view. So let's create a 4x3 array of ones. X is a 4x3 array of ones. And we are reshaping it into 2x6 using view. Using the view method, we are reshaping x. So x dot view 2,6. Okay, notice that when reshaping, the reshaped array and the original array should have the same number of total elements. Here there is 4 into 3, 12 elements. 2 into 6 is also 12. Otherwise, we cannot reshape and Pytorch will return an error. So another way you can reshape is, see this, see this x dot reshape. X is, remember, x is this 4x3 array of ones. I am reshaping like this, x dot reshape minus 1, 6. So what does this minus 1 means? Minus 1 means infer the value, infer this value from the other dimensions. Here I have mentioned 6 and I know that x has 12 elements in total. So Pytorch infers this minus 1 to be 2. Okay. So again, this is same as writing x dot reshape 2, 6. Okay, I have specified only this, the number of columns. So what should be the number of rows so that the total number of elements is 12? It has to be 2. So that way you can put minus 1 when you are unsure, when you want a specific value for one dimension and you don't care about the other dimension, you can put a minus 1 there. What about x dot reshape minus 1? Dot reshape minus 1, we are giving only one dimension. So that means we are reshaping, we want to reshape x to a one-dimensional array and we are not specifying the number of elements, minus 1, infer. We are telling Pytorch to infer the number of elements. So it will return a 12 element one-dimensional array. So let us create some more data. Torch.tensor 1, 2, 3, 4. It's a 1D array having 4 elements. Now, one thing you should remember is this is a 1D array. Now, if I make y is equal to x dot view 1, 4. Okay, and let us also print y. This might, x and y might seem the same, but they are not the same. X is a 1D array while y is a 2D array. See, if I type x dot shape here, you will see simply 4, because x is a 1D array having 4 elements. Only one entry here, 1D array. But if I type y dot shape, it is returned as 1, 4. Again, this might cause some confusion for those used to MATLAB. MATLAB has no such distinction, and it might take some time to use to. But once you have gotten used to this, it's all very consistent. So they are not the same. Okay, so and you can see that they are different by, if you carefully examining the output for x and y, you can see that here there is only one pair of parentheses, but here there are two. So that means y is a 2D array. Now we can convert x was this. We can convert x to a column tensor by like this, x dot view 4, 1. That means 4 rows and 1 column. 4 rows and 1 column. Okay, you cannot transpose 1D arrays. If you try to transpose 1D array, the result will be the same. Okay, the result will be the same. You can transpose only 2D arrays. Okay, so as you can transpose using dot t, or you can use the full method dot transpose. Okay, so many Python libraries images are stored as height, width channels. Most of us are used to this form of representation. Images stored as a 3-dimensional array with the dimensions representing the height, width, and channels. But Pytorch prefers to deal with these in this order, different order: channels, height, width. Okay, so when you want to input an image to some neural network uh, created using Pytorch, you will have to change the order. You will have to convert this height width channel representation to a channel's height width representation. For that, you can use the permute method. Let us create some image, random image, torch.rand 453. And suppose this represents a 4 by 5 image, 4 by 5 RGB image, height, width, channels, 4 by 5 RGB image. But this image cannot be given to Pytorch because Pytorch wants channels as the first dimension. So what we can do is I can permute img.permute 2, 0, 1. Okay. So if these are 4, 5, and 3 are the dimensions 0, 1, and 2, I am telling to put the dimension 2 first, then dimension 0, then dimension 1. Okay. So the result of this will be 3, 4, 5. The shape of this permuted tensor will be 3, 4, 5, 2, 0, 1. Okay, so here the dimensions, this is dimension 0, dimension 1 and 2. Put so 2 put 2 first. So that way. So another thing, neural networks processes images in batches for efficiency. Often we send images to neural networks in batches rather than one image at a time for efficiency, to make most use of the GPU resources. So Pytorch expects batches of images in this format: batches, channels, height, width. Batches, channels, height, width. But if you have only a single image and we want to apply that image to the input that image to the neural network, we can convert it into a batch of one image using this method, unskews method. So what this does is unskews method adds dimension of size 1 at the indicated position. Okay. So now image underscore t is a 3 by 4 by 5 tensor. Now if I add this, if I do this on img underscore t dot unskew 0, I am telling to insert a dimension of size 1 at position 0. Insert a adds a dimension of size 1 at the indicated position. And the indicated position is 0. So at position 0, add a dimension of size 1. In the shape you should see a 1 by 3 by 4 by 5. So this Pytorch will interpret as a 4 by 5 image with 3 channels and a batch having a single image. And conversely, skews returns a tensor with all the dimensions of input tensor of size 1 removed. If you skews this, all dimensions with size 1 will be removed with the skews. Now, we already saw some examples where Pytorch coexists very harmoniously with the Numpy. And we'll see, now we'll see that converting a torch tensor to a Numpy array and vice versa is very easy. For example, I have a torch tensor, torch a equal to torch dot 1's 5. This is a 5 element array having all ones. I can convert this tensor to a numpy array like this: a dot numpy, a dot numpy, a, apply the numpy method on a. That b will be a numpy array. B will be a number. You can see that this array. Earlier we saw tensors, isn't it? So this array tells that B is a numpy array. But here again, both objects will share the same memory location. So changing one will also change the other. Even converting to numpy has not uh, has not made Pytorch do a memory copy. These Pytorch and Numpy are all very reluctant in doing memory copy because they are designed to work with very large dimension data with millions of elements. Okay, so memory copying is the last resort. Only if we explicitly tell to copy in memory, they will copy data in memory. They will go to the they will try their best to avoid copying. Okay, think of performance. Okay, copying millions of bytes in memory is a very expensive operation. And so A is a tensor, 5-element tensor of all ones. Now if I use this method, add underscore 1. Okay, so I am telling to add 1 to all elements of A. Now this method might appear strange because of the trailing underscore. So there are some methods with a trailing underscore that tells us that that will result in an in place operation. So this a dot add underscore 1 will change A. It will not return any result. It will not return any result, but will change A in place. It will add 1 to all elements of A. So you see that A changed in place. Okay. But B also is changed. B was what we created by converting the tensor A to numpy array, but B is also changed. Okay, so 2 points here that you have to remember. Methods which have a trailing underscore, they are like a warning to tell us that it is an in place operation. Similarly, converting numpy array to tensor is also easy. Earlier we converted from tensor to array. We can do the converse also very easily. So we create an array, numpy array of ones. The command to do that is torch.tensor a. Torch.tensor a. It will accept the tensor method will accept numpy arrays also. Originally, in the initial cases, we created tensors from Python list. Instead of list, we can also give numpy arrays. Okay. B is a tensor having the same elements as A. Okay. Again, we have to be careful while modifying. If we modify A, B also is B is what happened here. A is once A. This creates a new object. Mistake in this cell. So, as I mentioned at the output, at the outset, one of the advantages of Pytorch tensors is their ability to accelerate tensor operations using the power of a GPU. Okay, so you can check that if Pytorch detects a GPU on your computer by this command, if torch.cuda is available. Okay, so this line will return CUDA if the GPU is available. Otherwise, it will return CPU. So on my computer, I have a small GPU. So this shows CUDA. Okay. So now let us see how we can do tensor operations on the GPU. So let us first create a tensor, 2 by 2 tensor X. Then by default, these all tensors are created on the CPU or the main memory. But you can move them to the GPU. If a GPU is available, you can move them to the GPU. How? Like this. X is now on the CPU, but using this to method, x dot to device, I can move to the CPU. I can move x to the device, which is now CUDA in my case. Similarly, you can also directly create a tensor on the GPU. That this shows such an example. Torch.once device. You can specify the device when creating this. I think there is some mistake here. Let us specify the size, I think. Okay, so here I am creating the tensor directly on the GPU because device is CUDA. Devices, and then I can add. Then I can add x and y. Then I can add x and y. So this addition was performed on the GPU. But it might seem that this took more time than running on the CPU, isn't it? When I run this, it appeared that now it's fast, but first time it was slow. The reason is that moving data from memory to from CPU to GPU is an expensive task. So for this simple addition, it wasn't worthwhile at all to move the computation to the GPU. It took more time because moving X and Y to the GPU was expensive. But when you have to perform millions of computations, we can harness the power of the GPU. Moving to the computations to the GPU will be advantageous, but not for this simple example because that moving of data from CPU to GPU is expensive. Okay, so now the result is also by the X and Y were in the GPU. So Z is also should also be on the GPU, isn't it? Z should also be in the GPU memory. Now, if I try to convert Z, the tensor Z to Numpy, I will get an error. The reason is that Numpy cannot handle GPU tensors. You can't convert CUDA device type tensor to Numpy. So for that, in order to convert Z to a Numpy array, you have to first move the tensor to CPU, and then convert to Numpy. Okay. So that worked. So Z is a tensor on GPU. So using this to method to CPU, I moved Z to the CPU, then converted to Numpy. Numpy does not support GPU operations. Okay. And the second major advantage of Pytorch tensor is automatic differentiation. Okay, so I think these two features are better for Pytorch compared to TensorFlow. In TensorFlow, in Pytorch, we have to explicitly move to GPU, isn't it? We have to, using the to method, we have to explicitly move the data to GPU if you want to use GPU. But I think TensorFlow, as far as I know, it assumes if a GPU is present, it assumes that you want to do the computation on GPU. It might not be the best thing to do always. Okay. So I think this gives you better control. Explicitly moving to GPU is possible in Pytorch only. That's what I believe. I may not be 100% right. Now the second major advantage of Pytorch is it provides automatic differentiation, because differentiation comes a lot when you train neural deep learning networks. You always have to differentiate perhaps the loss function with respect to the millions of parameters in the network. You will have to do millions of differentiations. Okay, so to facilitate that, Pytorch provides automatic differentiation. Let's take a look at what that is. Pytorch tensors can remember where they came from in terms of the operations and parent tensors that originated them, and they can automatically provide the chain of derivatives of such operations with respect to their inputs. Maybe you didn't understand much. Don't worry, these examples will clarify that. So suppose you want to compute the derivative of the function y equal to x square at x equal to 2. You have this function y equal to x square. You want to compute the derivative at x equal to 2. Derivative of y dy by dx at x equal to 2. That is, you want to compute dy by dx at x equal to 2. So first thing that you have to do is you have to create a tensor and set the parameter requires gradient to true. Every tensor has a parameter requires underscore gradient, which is by default true, false. By default, it's false. And if you want to do some differentiation on the tensor, you have to set that parameter to true. And that's what we do here. X is equal to tensor 2. X is 2. Assume x is 2. And I set the parameter requires gradient to be equal to true. Okay. So by doing this, I am telling Pytorch to track all operations on this x. If I compute y equal to x square, y is a function of x. And then again, if I compute some other function z using y, say z is equal to y into 3 plus 2. Okay, so z is also a function of x. So that all will all those operations that Pytorch does on the tensor x will be tracked, so that we will be able to compute the derivative of any function of x with respect to x. For example, dy by dx or dz by dx, all can be automatically available. The derivatives will automatically be available. Okay, so the requires grad argument is telling Pytorch to track the entire family tree of tensors resulting from operations on x. In other words, we can automatically compute the derivative of any tensor that will have x as an ancestor, not only y. If you define another function of say z is equal to some f of y, z will also be a function of x. So we can compute the derivative of z also with respect to x. So that's പറയുന്നത്. We can automatically compute the derivative of any tensor that will have x as an ancestor. The value of the derivative will be automatically populated as the grad attribute of the x tensor. Let us look some examples. So we already created x here. Its value is 2, but we have additionally set requires grad parameter to be true. Now let us create a function of x, y equal to x square, y equal to x square. So that is also, I didn't run the cell, I compared using some previous value of x. So x is 2, this here requires gradient is true. Now y is 4, x square is 4, y is 4, but it shows a gradient function. And if I check y dot requires gradient, that also is true, because using y we can generate more function. So we will need to compute the derivative with respect to y also, because in order to compute the derivative of z with respect to x, we will use the chain rule. So dz by dx will be computed as dz by dy into dy by dx, chain rule. So y automatically the requires grad parameter of y is also becomes true. Now let us take the derivative of y with respect to x at x equal to 2. എന്താണ് അതിന് ചെയ്യേണ്ട അതിനുള്ള കമാൻഡ് ഇതാണ് y dot backward will compute the derivative of y. Will compute the derivative of y. Y is a function of x, so it will be with respect to x. And if you look at x dot gradient, and remember that derivative of y with respect to x will be saved in the gradient attribute of x. So you see that dy by dx at x equal to 2 is 4, isn't it? Y equal to x square. So dy by dx is 2x, and at x equal to 2, it is 4. So you see that x dot gradient is 4. Okay. So let me recall what we have to do. If we want to track all operations on it, if you want to compute the derivative with respect to some tensor, you have to give the request gradient equal to true, that parameter. Then in order to compute the derivative, you have to call y dot backward. This is what actually computes the derivative, and the derivative with respect to x will be populated in the grad attribute of the x tensor. Okay, grad attribute of the x tensor. Now, one thing, one peculiarity is that the auto gradient calculation does not reset the gradients automatically. It accumulates by default. For example, if you compute y again and differentiate again and check the gradient attribute of x, you see that now it is 8, because the gradients are accumulated by default. They are accumulated. Original first time we did, the gradient attribute of x became 4. Second time we did the differentiation, the gradient accumulates. So if you don't want accumulation, you have to specify, you have to explicitly give the dot grad dot 0 underscore. So we have to zero out the gradient by giving x dot grad dot 0 underscore. Then if you check the gradient, it will be 0. Okay. So by default, all tensors with required gradient equal to true are tracking their computational history and support gradient computation. However, there are some cases when we don't need to do that. We can stop tracking computations by surrounding our computation code with torch.no gradient. And sometimes we need that. Even though the request gradient argument of a variable is true, we may not want to track gradient for some case. A specific example is we have trained the network and we have set the request gradient attribute for all parameters to be true, because we want to compute the gradient of the loss with respect to all the parameters. So we have set the request gradient attribute of all parameters to be true. But once we have trained and when we are testing the network, we don't want gradient computation, because during testing we are not updating the weights. So we don't need gradient computations while we are testing the network. So in such situations, you can use this with torch.no gradient, and whatever is enclosed within that block will not do gradient computation. Okay, so originally y request gradient was true because x is an ancestor of y, x, so y true. But within this block, if you print y dot request gradient, that is false. Okay, so we'll see this later. All these things were backward will be no gradient. We will see when we train neural networks. Okay, so another way to achieve the same result is to detach method on the tensor. Rather than using this block, you can detach method on the tensor if you don't want to track the gradient. So let us do some practice and let us determine the derivative of y equal to 2x cube plus x at x equal to 1. We want to compute dy by dx at x equal to 1. So എന്താണ് ആദ്യം ചെയ്യേണ്ടത്? First of all, what we have to do is we have to create the tensor x, isn't it? X is equal to torch dot tensor. Value of x is 1, isn't it? Value of x is 1, and we have to specify the requires grad attribute to be true. Requires grad attribute to be true. Then we can compute y is equal to 2, no, right here, 2 into x. Two x cube plus x, isn't it? Y is equal to 2x cube plus x. Okay, so we have computed y. Then എന്താണ് ചെയ്യേണ്ടത്? dy by dx ആണ് വേണ്ടത്. ഏതിൻ്റെ ആണോ ഡെറിവേറ്റീവ് വേണ്ടത്, we have to call the backward function on that. Y dot backward. Okay, so and what will happen? Dy by dx will be computed and that will be deposited in the grad attribute of x. Bitwise XOR. Where did I make the mistake? 2. Oh, sorry, this is not the exponentiation operator in part. So you should see 2x cube plus x. So derivative should be what? 6x 3x square. 6x square, isn't it? So 6x square plus 1. At x equal to 1, 6x square plus 1 will have value 6 plus 1, 7, isn't it? And we can also calculate partial derivatives. Consider the function. Am I audible?
Yes.
So we can also compute partial derivatives using the automatic differentiation in Pytorch. So consider this function f of uv is equal to uv plus v square. When let us see how we want to compute the partial derivative of f with respect to u as well as v. So we create first u and v. U is equal to torch dot tensor 1. Requires gradient true. V also we set requires gradient to be true. Then f, then compute f. So we have the value of f. F is equal to uv plus u square. So value is 3. uv plus v square is 3. So and we want to compute df by du and df by dv. So we call f dot backward. Okay, f dot backward first. F dot backward computed. Now what happens? Derivative of f with respect to u, that will be deposited in u dot grad, and the derivative of f with respect to v will be deposited on v dot grad. So that is for shown in the calculation here, and the derivative of f with respect to v is 1 as shown here. Okay. So try to determine the partial derivative of the following function. So the solution is also here. So I am skipping this so that we can move on to the next problem. Okay. So let us move on to a simple linear regression example to illustrate some features of Pytorch, including this automatic differentiation. We will take a simple linear regression example. But you know that there are two major types of supervised machine learning problems. They are classification and regression. They are the two major types of supervised learning problems. And in classification, we try to predict a class label, which is a choice from a predefined set of possibilities. Second class of supervised machine learning problem is regression. Now, in regression, we try to predict a continuous value rather than a discrete value, as in the case of classification. In regression, we try to predict a continuous value, or in mathematical terms, a real value. In programming terms, we try to predict a floating point number. Okay, so an example would be, suppose we have so we have some data. So we have some data connecting engine size and carbon dioxide emissions for a car, and if we want to, from that data, we want to predict the CO2 emission of a car given its engine size. Okay, so CO2 emissions is a continuous value. Okay, so another example would be, we are trying to predict the sales, annual sales for a salesperson from his experience, education, and age, etc. So that would also be a regression problem, because annual sales will be a continuous value. Okay, so regression itself can be classified into simple regression and multiple regression. Okay, in our first example where we try to predict CO2 emission from engine size, that is an example of simple regression, because there is only one independent variable. Okay, from engine size only we are trying to predict the CO2 emission. On the other hand, in the second example, I said if we try to predict the sales of annual sales of a salesperson from many different independent variables like his experience, age, etc., that is an example of a multiple regression. Okay, so to give another example, if you try to predict CO2 emission from engine size, number of cylinders, age of the car, that will be a multiple regression. So because we have three independent variables from which we have to predict the dependent variable, which is the CO2 emission. So that is one classification. We can classify into simple regression or multiple regression. Simple regression is when we have only one independent variable. Dependent variable will always be one, whether it is simple regression or multiple regression. When we have only one independent variable and one dependent variable, we have simple regression. And when we have multiple independent variables from which we have to predict the dependent variable, we have the case of multiple regression. Also, regression can be linear or non-linear. Okay, so that depends. Linearity of the regression depends on whether we have a linear relationships between the input and output, between the independent variable and the dependent variable. Okay, so we will consider simple linear regression. So simple linear regression means, simple here means we have only one independent variable. Linear means we are assuming a linear relationship between input and output. Okay, so to make things a little more concrete, let me try to show. Say we have some data. This is the engine size of a car, and this is an independent variable, and the dependent variable is CO2 emissions, and we have some data. Here. We have some data. Okay, so given this data, the problem in simple linear regression is, given this data, given this historical data, how can we predict the CO2 emissions of a new car whose maybe it's not even manufactured, or it's some car whose CO2 emission has not yet been measured. Okay, so we have to do that from this data. Given all we have is this data from some measurements, we have taken on some cars. From this, we have to make the make a prediction of CO2 emission for a new car. So here engine size is the independent variable and CO2 emission is the dependent variable. We have to predict the CO2 emission from engine size. So how to do that? How can we do that? So again, we are assuming a linear regression. We are assuming a linear regression. So that means we are assuming a linear relationship between engine size and CO2 emissions, isn't it? We can, from this data, you have to look at the data and determine whether linear regression would be applicable or not. Now, but this the data that we have, it looks like there is a linear relationship between engine size and CO2 emission. As engine size increases, so does CO2 emission. So this seems to be a case for linear regression. Okay, so in linear regression, what we do is we given this data, we fit a line. We fit a line because we are assuming a linear relationship between the independent variable and dependent variable. We will try to fit a line given this data. We will, sorry, that wasn't the best line, but anyway, suppose say this is the line that we have fitted. Okay, we fit a line. Now, say assume that we have fitted a line with this data. Now, once we have fitted a line to the given data, we can make predictions. How? Once we have this line, we can make predictions, isn't it? For say for a new car, this is the engine size. This is the engine size for some new car. Then from this line, I can make the prediction that the CO2 emission for this car will be equal to this. If I have this line. Okay, so now the question is how to find the line, how to find the best fit line, the line that best fits the data. Now, determining the line means we have to we have to find the parameters, the slope and bias for the line. We have to find the slope and bias. We have to say we have this line y is equal to wx plus b. We have to find w standing for weight and b for bias. Okay. So now, since we don't have any data, let us create some artificial data. Let's create some artificial data. So the independent variable is called, we call it as x. This is x. Independent variable. This is x and this is y. Okay. So let us create some data like this. Artificially create some data, but in a real world problem, that data will be measured. So we create x from -3 to 3, y is 2x minus 3, and we add some noise. We add some Gaussian noise. It's an assumption in linear regression that the noise is Gaussian. So let us create that and let us plot the data. Okay, so we plot the data. So I have shown the line also here, but in a real world problem, we would have only this data, the red dots is all we have. Using those data, we have to find the line that best fits the data. Okay, but since this is an artificial data, I already know that the slope is 2 and the y-intercept is -3. Okay, but remember, in real world problem, we will not have the line, and the problem is to determine the slope and y-intercept for the line that best fits the given data. Okay, so from the data, we observe that y is linearly related to x. So we decide to model y as a linear function. So we decide to apply simple linear regression. Simple because we have only one independent variable, the engine size. Linear because they seem to be, from the data, they seem to be related in a linear fashion. So you selected a linear model y equal to wx plus b. So to create a simple linear regression model to predict y from x, we feed our training examples, and the regression algorithms learns the parameters that make the linear model best fit to your data. Stated differently, the linear regression will learn the parameters, the slope and the intercept, okay, of the line that best fits the data. This is called training the model. In our example, the parameters to be determined are the slope and intercept of the best fit line. So once we have the best fit line, we can easily make prediction, isn't it? We can easily make predictions like this. The predicted quantity will be we'll call as y hat. Using this function, we can make predictions. So simply y equal to y hat is wx plus b, like I showed here. This is how I make a prediction. This is x, and this is the predicted emission, y we call as y hat. Okay, so so how will I find this line? How will I find the best fit line? Okay, so assume that this is the best fit line. Assume that this is the best fit line. This red one is the best fit line. But I can see that from the training data, if I make predictions on the data that I already have, there are some errors, isn't it? For this sample, if I input this value of x, the predicted emission will be this. But there is some error here. There is some error. So for each data point, there is some error. For this data, there is this error. Here I have this error, this error. There is this error between the predictions and the data, isn't it? So we can see that the errors can be either negative or positive. So to make all errors positive, we take the square of the errors. And we determine the best fit line by minimizing the sum of all the squared errors. We minimize, we find the best fit line such that the fitted line should have the minimum mean square error. So we define the loss function as 1 by n sigma. What I call this is y hat. This is y hat, the predicted emission, but this is the actual value. This is the actual emission. Again, for this predicted emission is this, but this one is the actual. So there is an error between them. We want to minimize the errors, the total, the error over all the samples. I have to minimize the error. So I can define the error as sigma y hat minus y the whole square over all samples, I equal to 1 to n. I am squaring the error so that all errors are positive. Otherwise, the negative errors might cancel the positive error. To avoid that, I square all the errors. And this is what I want to minimize. Okay. So now this error will depend on the line, isn't it? If I choose a different line, like this, if I choose a different line like this will have more error, isn't it? In this case, these are the errors, and squared and this, I'll call this as MSE. The mean square error will be more if I choose this line instead of this line. Okay. So how will I find the best line? Should I randomly pick many different lines and compute the mean square error for each of these lines? Should I try many different lines and try to minimize and try to pick the line which has the minimum error? No, that is not the way we do this. So actually, there are two ways to solve this problem. One is the analytical way. We can mathematically solve this using some equations called the normal equations. We can analytically solve the problem. But then there is also a optimization method to solve this problem. We will be using the optimization method because that is what is applicable for more complex functions. This is a very simple linear function with only two parameters. But for very more complex functions, analytical solutions are not possible. Only a possibility is to resort to optimization methods, like deep learning problems. Even here we are predicting CO2 emissions given engine size. But in an image classification problem, we have to predict the class label given the input pixel values. That is a highly nonlinear problem. We cannot use analytical method to solve such complex problems. Only way is optimization problem, optimization method. So how can we use optimization to find the best fit line? We have to minimize this mean square error. Now it happens that we know that once we have the line, suppose assume for the moment that we now have the best fit line. We have this best fit line, and we know how. Once we have this best fit line, we know how to make the prediction, isn't it? We make the prediction as y hat is equal to wx plus b. Okay. Now, if you make this substitution here, you will see that MSC is equal to what? 1 by n sigma I equal to 1 to n wx plus b minus y the whole square. So we see that if you square this, you can see that MSC is a function of w and b, a quadratic function of w and b, isn't it? So we have this mean square error as a function of as a quadratic function of both w and b, the weight and bias, or the slope and the intercept. So let's go back to code. I think I may not have explained it clearly. Maybe the code will explain this a little bit better. Okay, so anyway, suppose we have this model. We have the best fit line. We can make predictions using this forward function, isn't it? Simply give the input and it will make the prediction w into x plus b, assuming w and b are the optimum weight and bias. So let's define that. And we already mentioned that the loss function. Before we can fit data with our model, we need to determine a measure of fitness. I mentioned that the best measure of fitness is the mean squared error. The loss function quantifies the distance between the real and predicted value of the target. The loss will usually be a non-negative number where smaller values are better and perfect predictions incur a loss of 0. The most popular loss function in regression problems is the mean square error. So let us define the loss function also. So this is called the criterion loss function. And then another predicted minus actual, y hat minus y square, and the mean, isn't it? So that's what the mean square error. This function computes the mean square error between the predicted values and the actual values. Okay. Now let us plot the loss surface to visualize the parameters. Let me run the cell and explain. Okay, so as we saw, the loss is a quadratic function of weight and bias. The loss is a quadratic function of weight and bias. So I can compute the loss for many different values of w and b, and that's what I have done here. I have made w to go from minus 15 to plus 15. Bias also goes from minus 15 to plus 15. And for each value of each pair of w and b, I compute the loss. How? For each value of w and b, I first compute the predicted value, then compute the error. So this is the loss or the mean square error, and that made a surface plot of that, and this is the loss surface, isn't it? So this is w, and this is b. This axis is b. This is w, and this is the loss function. So as we saw, we see that the loss is a quadratic function of w and b. That's why we see a convex surface here. So for example, if my w and b is this, if my w is minus 15 and b is minus 10, what will be the loss? W is minus 15 and b is minus 10, you will be here. So you can read off the loss. And you can see that the loss at somewhere here for some of these values for w and b, the loss is minimum for some these values of We already know what the values of optimum values of W and B will be, because we created our data artificially. We created the line W as 2 and B as minus 3. So we know that loss will be minimum for W equal to 2 and B equal to minus 3, somewhere here. Okay, so what I have done here is I have computed the mean square error for different values of W and B, and this shows the loss contour. The loss contour. So, on any of this contour, the loss will be constant. Okay, so for example, if I move along this contour, the loss will be some constant. For all these values of W and B, the loss will be some constant value. So higher loss, the minimum loss. So how do we find the, so what we want to find is the bottom of the surface where the loss is minimum. We want to reach the bottom of the surface somehow where the loss is minimum. We want to, bottom of surface means the corresponding values of W and B, that will make the loss minimum. And the common strategy we use is called a stochastic, gradient descent method. Gradient descent method. Okay, so suppose we are here. We find the gradient of the loss with respect to W and B. Okay, so at this point, say I am here. Currently I am having this line. This line corresponding to say B is minus 10 and W is equal to some other value. W is equal to minus 50. I am here. Okay. So I compute the gradient of the loss function with respect to W and B. So we can see that the gradient will be negative, isn't it? At this point, the gradient of loss with respect to W and B will be negative. So that tells, I want to move here. So that from that negative value of gradient, I will increase both values of W and B. Okay, so using gradient descent, I gradually will move to the bottom of the line. So that is what gradient descent. Maybe this 2D example, maybe I can explain with the 1D case. Uh, Say I have this data. I want to fit a line. Say I have say B is 0. Say if B is 0, I am fixing B to be 0, and I can adjust only W. In that case, different lines will be like this. B is fixed to be 0. I have no control over B. So these are the different lines that I can choose. Okay. So for different W's, this is W1, W2, W3, etc. I will have different losses. For example, corresponding to W2, we can compute all the losses and compute the mean square. We saw that the mean square, the loss will be a quadratic function of W. For this one parameter case, I don't have flexibility to change B. I have only flexibility to change W. So in this case, the loss will be a function of W like this, a quadratic function of W. So suppose currently I have chosen this value for W. And I have this loss. Then I compute the gradient of the loss. Dou L by dou W is computed. Okay, so since I am here, the gradient will be negative. The gradient is negative means I have to increase W. So I will, the next step, I will move to this position. Here also the gradient will be negative. So if the gradient is negative, increase W. That's what we will tell that's what the gradient descent algorithm is. Again, so gradually I'll move to the bottom of this curve, from which I can find the optimum value of the weight or the slope that will minimize the loss. On the other hand, if I had started here, I had this value of W with me now. Now the gradient of the loss with respect to W here is positive. Dou L by dou W is positive here. So if I have a positive gradient, that tells me I have to decrease W. So I'll make a step and I'll gradually I'll move to the bottom of the curve. So this is a convex optimization problem. Another point I would like to add is how much should I step, and that is determined by what is called the learning rate. If the learning rate is high, the steps the sizes will be large. If learning rate is small, it will make small steps. So anyway, let's come back to our code, and this is how this is the loss surface. How loss varies with the W and B for our example, isn't it? So we can see that the minimum loss is here, and how we will apply gradient descent is, suppose we will choose some initial value of W and B here, maybe here. Okay, then I will compute the gradient of the loss with respect to W and B. What I will find is that both the gradients are negative. So that tells me to increase B and W by some delta. So I will move here. Again the gradient will be negative. So again tells me to increase B and W. So gradually I will reach the bottom. I will reach the optimum values of W and B. Okay, so we want to compute the gradient of the loss. Now let us move on to training the model. Okay, so let's recap what we have done. We have created some artificial data, and this is the data. Our problem is to find the best fit line. In stated differently, we have to find the slope and y-intercept for this line that best fits, so that we can make predictions about when we see a new x, we can make predictions accurately. Okay, so and how do I find this? I have to find the best fit line is defined as the one which results in the minimum mean square error. Best fit line will result in the minimum mean square error. Mean square error is the error between the predictions and the actual value. These small errors are there. All the errors are squared and their mean value is computed. That is the mean square error for this data. For this line, for a different line, mean square error will be different. It will be more. Okay, so that is how we define the fitness criteria, best fit criteria. We have to minimize the mean square error. We have to find the slope and bias that will minimize the mean square error for the line. And how do we find the best parameters? We do so by an optimization approach, specifically the what is known as the gradient descent approach. We find the gradient of the loss with respect to both W and B. And in this example, it happens that they are functions of they are quadratic functions, and we have a very fine convex optimization problem. We have a very well-defined minimum. But in deep learning problems, we will not have such well-defined minimums. Okay, so but this is a simple linear regression example, and we can use optimization to find the optimum values of W and B. Okay, so we define initial values of W and B. We pick W is equal to minus 15 and W is equal to minus 10. We know that these are not the ideal values. We know that 2 and minus 3 are the optimum values because we created artificial data. So anyway, we start with, in order to illustrate the training process, we start with W equal to minus 15 and B is minus 10. And we set the requires grad parameter of both attribute of both these variables as true. Why? Because we want to compute the gradient of the loss with respect to W and B. Using that gradient only, we are adjusting W and B. Okay, so then we define the learning rate. As I mentioned, learning rate is determines how much we step at each iteration. So we also want to track the history of the loss, how the loss changes and W and V changes. We expect the loss to decrease, isn't it? Now we have the training loop. We using this we can train the loop. Okay, so we make 10 iterations, and it's this training loop is not very difficult to understand. So we choose some initial value നമ്മൾ choose ചെയ്തല്ലോ ഡബ്ല്യുവിൻ്റെയും ബിയുടെയും -15 10 choose ചെയ്തു. Using those values we make the prediction. Y hat is the predictions are. Remember ഇതിൽ നമുക്ക് ആ മൊത്തം ഡാറ്റ ആണ് കൊടുക്കുന്നത്. X ഒരു കോളം വെക്ടർ ആയിട്ടാണ് നമ്മൾ ഡിഫൈൻ ചെയ്തിരിക്കുന്നത്. മൊത്തം ഡാറ്റ കൊടുക്കുന്നു. So that will compute all the outputs corresponding to all the inputs, all the predictions based on our initial values of W and B, okay, which we have chosen as -15 and 10. അത് കഴിഞ്ഞ് എന്ത് ചെയ്യും? We compute the error. We compute the mean square error. Y hat 1 by n sigma y hat minus y the whole square. അതാണ് error between the predicted values and the actual values. തമ്മിലുള്ള എറർ കമ്പ്യൂട്ട് ചെയ്തു. പിന്നെ നമ്മൾ ആ എറർ നമ്മൾ ഒരു സേവ് ചെയ്തു. നമുക്ക് കാണാൻ വേണ്ടി we save the loss in this iteration in this list. ഒരു ലിസ്റ്റ് നമ്മൾ എംപ്റ്റി ലിസ്റ്റ് ആദ്യം ക്രിയേറ്റ് ചെയ്തിട്ടുണ്ട്. അതിലേക്ക് നമ്മൾ കറന്റ് ഐറ്ററേഷനിലെ ലോസ് സേവ് ചെയ്തു. റിമെമ്പർ ലോസ് എന്ന് മാത്രം എടുത്താൽ ഇതൊരു ടെൻസർ ആണ് റിട്ടേൺ ചെയ്യുന്നത്. ആ ടെൻസറിന്റെ ആക്ച്വൽ ഫ്ലോട്ടിംഗ് പോയിന്റ് വാല്യൂ കിട്ടാൻ we have to use the item method. Also we want to maintain a history of W and B so that we can visualize how W and B changes. ഇനി എന്ത് ചെയ്തു? ലോസ് കമ്പ്യൂട്ട് ചെയ്തു. നമുക്ക് വേണ്ട എന്താണ്? We have to compute the gradient of the loss with respect to W and B. Gradient of the loss. So we have to call backward on loss. അല്ലേ? നേരത്തെ നമുക്ക് when we wanted to compute dy by dx we called y dot backward. Now we want to compute the gradient of the loss. So we call loss dot backward. ഇനി എന്ത് ചെയ്യുന്നത്? Now we update W and B based on the gradient value. W data is W data minus learning rate into W dot grade dot data. W dot gradeലാണ് അതിന്റെ gradient ഉള്ളത്. Dou L by dou W will be in W dot grade. Dou L by dou B will be in B dot grade. അതിന്റെ ഡാറ്റ വാല്യൂ എടുത്തു, ലേണിംഗ് റേറ്റ് വെച്ച് മൾട്ടിപ്ലൈ ചെയ്തു, ആൻഡ് we update the parameters slope and bias. അതുപോലെ ഇവിടെ മൈനസ് സൈൻ വന്നത് എന്താണെന്ന് മനസ്സിലായി? y നോട്ട് പ്ലസ്. അത് ഞാൻ ഇവിടെ എക്സാമ്പിൾ ഇവിടെ കാണിച്ചു. ഇവിടെ ആണെങ്കിൽ എന്താണ്? if you are at this point, ഇവിടെ ആണെങ്കിൽ the gradient is, if you are here, ഇവിടെ ആണെങ്കിൽ ഗ്രേഡിയന്റ് എന്താണ്? ഗ്രേഡിയന്റ് നെഗറ്റീവ് ആണ് അല്ലേ? ഗ്രേഡിയന്റ് നെഗറ്റീവ് ആണ്. ഗ്രേഡിയന്റ് നെഗറ്റീവ് ആകുമ്പോൾ നമുക്ക് ഡബ്ല്യുവും ഇൻക്രീസ് ചെയ്യാണ് വേണ്ടത്, ഇങ്ങോട്ടാണ് നീങ്ങേണ്ടത്. അപ്പം ഗ്രേഡിയന്റ് നെഗറ്റീവ് ആണെങ്കിൽ വി ഹാവ് ടു ഇൻക്രീസ് ഡബ്ല്യു. സോ ഇഫ് DL by dW is less than 0 we have to increase W. On the other hand, ഇവിടെ ആണെങ്കിലോ ഗ്രേഡിയന്റ് dou L by dou W പോസിറ്റീവ് ആണ്. അപ്പൊ പക്ഷെ നമുക്ക് മൂവ് ചെയ്യേണ്ടത് ഇങ്ങോട്ടാണ്. സോ ഇഫ് dou L by dou W is greater than 0 we have to decrease W. അപ്പൊ അതുകൊണ്ടാണ് ഇവിടെ ഈ മൈനസ് സൈൻ വരുന്നത്. നോക്കിക്കേ, ഇത് ഗ്രേഡിയന്റ് നെഗറ്റീവ് ആണെങ്കിൽ എന്ത് ചെയ്യണം? നമുക്ക് W കൂട്ടുവാണ് വേണ്ടത്. ഗ്രേഡിയന്റ് നെഗറ്റീവ് ആണ്. സോ ദിസ് ഇസ് നെഗറ്റീവ്, P മൈനസ് സൈനോട് വരുമ്പോൾ പ്ലസ് വരും. സോ W will be increased. അതുപോലെ തിരിച്ചു. സോ ദിസ്, I hope this minus sign is clear. And also we have to, after each iteration we have to set the gradient to 0, because as I mentioned, by default Pytorch accumulates the gradients. So we have to zero out the gradients after each iteration. Okay, so let us run this training loop for 10 iterations. So I did not define this. Okay, and it has been computed, and let us do some visualization. So this shows how we have saved the loss history in this list. So we plot that, how we see how the loss changes at each iteration. Okay, so we see that loss decreases. So our gradient descent works. We have manually implemented gradient descent. In when you come to neural networks, you will not have to go into such low-level detail. There are functions, but just to illustrate how all this happens under the hood, I have written this code. So we see that loss decreases like this, and I also on the low surface contour, I plot how W and B changes. These were the initial value of W and B. I have superimposed W and B on the low surface contour. ഇവിടെയാണ് ആദ്യം നമ്മൾ ചൂസ് ചെയ്തത്. W was എന്താണ്? W was -15 and B was -10. So we have a red cross here. അടുത്ത സ്റ്റെപ്പിൽ എങ്ങോട്ട് പോയി? ഇങ്ങോട്ട് പോയി. സോ ബിക്കോസ് അവിടെ ഗ്രേഡിയന്റ് നെഗറ്റീവ് ആയിരുന്നു അല്ലെ, ഗ്രേഡിയന്റ് നെഗറ്റീവ് ആയിരുന്നു, അതുകൊണ്ട് ബോത്ത് W and X were increased. So വീണ്ടും അങ്ങനെ after 10 iterations we can see that we reached almost the optimum, because from our data we know that the best values are the actual data was created from by adding noise to 2x minus 3. So W2 B minus 3 ആണ് best values. അപ്പോൾ അതിന് അടുത്ത് എത്തിയതായിട്ട് നമുക്ക് കാണാം. Okay, so we see that what has been learned is W is 1.9788. Best values 2 and this is 3. And tensor B is minus 3.8. It's a learned value, even though now there is little more to cover, but I think I will cover it tomorrow. Linear regression as a neuron model will be covered later, next class. And if you have any questions, please ask. I will stop my presentation. Thank you. At the time,
Thank you, sir, very much. Actually, it's taking so much effort, this much time without any break. Actually, I think sir will can take some break in between, but continuous class. I think it will helpful for everyone. Actually, I also don't know what is Pytorch and everything, and I am first hearing and this type of library. Thank you, sir. If anyone have doubt, then they can ask, or we can stop here. Or
I think it was okay.
Thank you.
നാളെ ഇതിന്റെ
ഇതിന്റെ കുറച്ചുകൂടെ ബാക്കി ഉണ്ടായിരുന്നു. അത് തീർത്തിട്ട് വേറെ ഒരു നോട്ട്ബുക്കും കൂടെ ഉണ്ട്. വേറെ ഒരു ന്യൂറൽ നെറ്റ്വർക്ക് ഇംപ്ലിമെന്റ് ചെയ്യുന്ന ഒരു നോട്ട്ബുക്ക് ഉണ്ട് നാളെ. ഇന്ന് ഇത് തീർക്കാമെന്നാ വിചാരിച്ചു, പക്ഷെ ഇപ്പൊ പിന്നെ ഇത്ര ആണ്ട് അടുത്തു. കുറച്ചും കൂടെ ഇത് തുടങ്ങിയിട്ട് ഇതാദ്യം കംപ്ലീറ്റ് ചെയ്തിട്ട് വേറെ ഒരു നോട്ട്ബുക്ക് ഉണ്ട് എന്റെ, അതിലും കുറെ ഉണ്ട് തീർക്കാൻ തോന്നുന്നു. ഇവിടെ അത് ഓക്കെ നിർത്തട്ടെ സാറേ.
okay. Thank you, sir, very much. Feedback session I sent to mail to everyone. Please fill it today itself. Thank you everyone for this. Actually, it was very much late also, but most of them are present there. So thank you very much for everyone.